Hello students, let's resume section 3, general solutions. And we're done with 3.1 and 3.2. And let's begin 3.3, lemma. And what does it say? The linear combination of y1, y2, all the way to yn is constantly 0 is equivalent to the same linear combination of those column vectors is constantly 0 vectors. Do you recognize these column vectors? y1, y1 prime, y1 double prime, y1 triple prime, and so on, all the way up to n minus first derivative of y1. Same for y2, same for y3, all the way up to same for yn. Haven't you seen these column vectors before? You have. Those are the column vectors of Wronskian matrix. In other words, we're headed toward Wronskian. Now, did I say Wronskian is something I wouldn't put too much emphasis in this course? That's right. That's why I'm doing this in this optional video. Anyway, here we go. These two are equivalent. Let's prove it. One direction is rather trivial. Which one? If this column vector's condition is true, then the scalar condition is true. That direction is trivial. And here's the proof. All you have to do is to look at the first component. You see, for this column vectors, everything has to be true. In particular, first component, c1y1 plus c2y2 plus blah blah blah, cnyn should be equal to 0. And that's precisely what this condition says. How about the other direction? That could be a bit trickier, but not too much as a matter of fact. All you have to do is to take the derivatives repeatedly. Here we go. Let's follow the same color coding. First row, let's keep it blue. So c1y1 plus c2y2 plus all the way up to cnyn is constantly equal to 0. And from here, let's take the derivative. This is constantly equal to 0, so take the derivative of constant 0 is, of course, 0. But then again, what's the derivative of this first row? That is the second row. c1 y1 prime, c2 y2 prime, plus all the way up to cn yn prime. So the second row, is also 0. Where are we so far? Yep, c1 y1 prime, c2 y2 prime, plus all the way up to cny prime is equal to 0. That's where we are so far. Next, take the second row and take the derivative of this constant 0. Derivative of constant, always 0. But then again, what is this? The derivative of the second row? It is the third row, given by all the second derivatives. What's happening here? Why can't I highlight all this appropriately? Okay, I succeeded. The second derivatives are coming from the derivatives of the first derivative, or the second row. So here we go. No derivative, first row, take the derivatives, and then we have the second row. Take the derivative, we get the third row. Do it again, we get the fourth row. Do it again, until we hit the end. N minus first derivatives. We have them here, in the last row here. They were 0. That completes the proof. Conclusion. Linear combination is constantly equal to 0, is equivalent to this linear combination of column vectors is constantly equal to 0. Is it useful? We're getting there. Please remember these are related to Wronskian. Okay, next. Linear independence. y1 through yn are linear independent is equivalent to these column vectors are linearly independent. Yeah, that's pretty natural here, because after all, linear independence means this constantly equal to 0 implies all the coefficients are 0. And we are talking about the equivalence there. So we're going to end up with this kind of logic. So what do you have here? y1 through yn are linearly independent. What does that mean? Linear combination is constantly equal to 0, implying c1 through cn are all 0. Coefficient are all 0. Now, this highlighted part, highlighted in red, is equivalent to the vector expression as we proved in the lemma. So the second line and the third line are equivalent because the red part and that red part are equivalent to each other. And how about the third line? That's nothing more than the definition of the linear independence of those column vectors. So we have it. The linear independence of those functions and the linear independence of these column vectors are equivalent. Now, are we ready for Wronskian? Okay, let's begin. y1 through yn be solutions of the homogeneous equation. Alright. If they are linearly dependent solutions, then determinant is constantly 0. Constantly 0 for all t values. Okay, how do you prove that? All you have to do is to prove the linear dependence, and that's about it. Let's see. y1 through yn are linearly dependent. That means we can find out c1 the column, c2 the column, and all the way to cn the column is constantly 0. That means for any t, this vector and that vector and the third column vector and in the end nth column vector are linearly dependent. So the determinant has to be 0. This is standard result of linear algebra. Some people took it, some people maybe didn't, but we are going to prove that in linear algebra. It's actually difficult to prove, but it's well-known theorem, useful in all kind of cases. So it's going to be necessary for everybody to remember those. Now let's go to the other. How about linearly independent case? For dependent, Wronskian determinant was constantly 0. For independent, no, but it's a bit surprising because it says not equal to 0, not only that, for every t. What does that mean? Wronskian determinant is either constantly 0, which we proved, or never 0, which we will prove, which is a bit harder. It's kind of surprising because not constantly 0 can mean sometimes 0, sometimes not 0. We have a graph of a function. Yeah, determinant is a one-dimensional function. So we have a graph of a function. And will it hit the x-axis once or maybe multiple times? This theorem says no. Either it is constantly 0, or it'll never hit the x-axis. Let's prove that. It's a bit difficult, but let's take one step at a time. Okay, we want to prove that this is non-zero for any t, so let's use proof by contradiction. Let's suppose that there is a certain t0 so that the determinant is indeed 0. And later we are going to prove that such t0 does not exist, therefore contradiction. But this is where we're going to begin. So the determinant is 0, which means these column vectors are linearly dependent. So these are linearly dependent, so we can form appropriate linear combination where not all C1, C2, not all coefficient is 0, where this linear combination is 0. Now without loss of generality, we can assume that C1 is non-zero. Why? What if C1 is 0, but say C17 is non-zero? In that case, we can simply switch the order and then rename, then all is well. Because it doesn't matter which order we do. And if we can always change the order without liking. That's what this without loss of generality generally means. So we can assume C1 is non-zero. So divide everything by C1 and then solve for this column vector. Yes, you can do that, and this is what we get. Flip everything to the other side, divide by C1, you get negative C2 over C1, and then this column vector, negative C3 over C1, and the third column vector, and all the way to the last one. Okay, we have it. Now, how will that help? Using the same linear combination, we just define a new function which we call y star. Y star of t is negative C2 over C1 y2 plus negative C3 over C1 y3 and so on. We define it like that. So this is true for arbitrary t. Now let's take the derivative, second derivative, third derivative, and so on. Then we are going to get this, and this is going to be true for all t, but in particular t0 as well. So we have this and that, this and that. What do you see? Right hand side are the same, right? Therefore, left hand side will have to be the same as well. So y1 t0 is equal to y star t0. y1 prime t0 is equal to y star prime t0, and so on. This left hand side is equal to this left hand side because right hand side are the same. So what do you get? y1 and y star share the same initial condition. And furthermore, both y1 and y2 are solutions. Why is y1 solution? We started all the way from the beginning. Why is y star a solution? Because of the principle of superposition here. y2 through yn are all solutions, and this is a linear combination of solutions of homogeneous equation. So this is also a solution. We proved it right here. So what do you have? Y psi solution, y1 is also a solution. They also share the same initial condition. By the uniqueness, they have to be the same function. Y psi and y1 are the same. So what do we get? For y star, it is defined by linear combination of the other functions. So y star and y2, y3, or the yn are linearly dependent, but y1 and y star are the same. So y1, y2, y3, all the yn are linearly dependent. That's what we get. We got linear dependence. That's a contradiction. We assumed from the beginning y1 through yn are linearly independent. And we ended up with dependent solution. Contradiction, which means this first condition, there exists a certain t0 so that this Wronskian determinant is 0. That cannot be true. Such t0 does not exist. In other words, Wronskian can never become 0. I don't know whether you could follow all this. It was really difficult proof, but we got it done. In the end, what did you get? Wronskian is either constantly 0, linearly dependent case, or never 0, linearly independent case. Are we ready for the final proof of this general solution theorem? Okay. We know this form is a solution. Now, is every solution of this form? This form is a solution. We did it in principle of superposition here. Okay, this form is a solution. Now, is every solution of this form? Let's prove that. Okay, let y of t be solution. And if y and y1, y2, all the way up to yn are linearly dependent, then we'll have some coefficient b0, b1. I mean, c is already selected, so I have to use some other character, b0, b1 all the way. Not everything is 0, so that the linear combination is constantly 0. Okay, all right. Now here's a typical trick in linear algebra. We'll claim b0 is 0. b0 is non-zero, excuse me, what did I say? If b0 is 0, if this is 0, then this one drops down because this is 0. And what do you get? b1, y1 plus b2, y2 all the way to bn, yn are equal to 0. But then again, these are linearly independent. So b1, b2, b3, bn, they're all 0. If we assume b0 is 0 and everything is also 0, what do you get? We have linear independence. That's not the case. That's not what you assumed. So it is b0 that should be non-zero. So from here, we can divide each term by b0. That's what we have over here. Divide by b0 and solve for y of t, and then what do you have? We have a linear combination like this. Y is negative b1 over b0 plus negative b2 over b0 all the way up to negative bn over b0. And what did you get? We got desired conclusion. Okay, all right, so far so good. Now what if these are linearly independent? Well, this was under the assumption these were linearly dependent. Okay, how about the other case, when these are linearly independent? In that case, by the lemma, these column vectors are linearly dependent. So put all those together and then go to just Wronskian determinant. Then that is, these are linearly independent. Yes, okay, independent. So Wronskian is always non-zero. However, this is impossible because the last row here is a linear combination of the others, as a matter of fact. You see? Let's see. Okay, yes. Yes. an and then all the n's derivative plus an minus 1 and then the second row all the way up to a1 times the second row and a0 times first row, everything together, then we have to have all the zero vectors. So what do you have? We have to have linear dependence here because of the ordinary differential equation. It says independence, so that is not the case. There goes contradiction, so we cannot have linear independence. And that completes the proof. General solution. In conclusion, what do we have? Every solution must be of this form.